Okay. So nitrogen is an explosive liquid, and this is its decomposition reaction, right? So when you explode nitrogen, you get a bunch of gas and a lot of energy. I'm going to try to balance this equation, and this one is a doozy for sure. So I think if you can crack this one, you can crack almost any equation. So let's take our inventory. 3, 5, 3, 9, 1 carbon, 2 hydrogens, 2 nitrogens, and then I see 5 oxygens. So who am I going to fix first? Let's see. I'm actually going to go ahead and fix nitrogen first and see how that works out for me, because 3 and 2 have a common multiple of 6, and I feel like that's going to give me problems down the road if I don't nail it now. So let me try that. So I'm going to say 3, and then I'm going to change this to 6. I'm going to say 2, and everybody here gets a multiplier. So we get 6, 10, 6, and 18. So that fixes my nitrogens. Let's see if I can fix my carbons next. So 6 carbons, so that's fixed now. And now I've added a bunch of oxygens to the mix. So now I have 12 oxygens, plus 2 is 14, plus 1 is 15. Okay, so carbon looks good, nitrogen looks good, and we only have one place where we can fix hydrogen. We have 10 hydrogens on this side, so let's put a 5 here, and then I get 10 times 2, sorry, 5 times 2 is 10, and then of course I add a bunch of oxygens. In this point, I'm going to say there's no shame in pulling out the 4-function calculator or just using your plain 4 functions on your scientific calculator to balance your equation, because oxygen can get funky. So we have 12 oxygens from the CO2 plus 5 plus 2. Now we have 19 oxygens. Okay, we're good on carbon, we're good on hydrogen, we're good on oxygen. Here's where this one gets tricky. We have 18 oxygens over here and 19 oxygens over here, but this is a diatomic gas, right? This is part of our uncle riff or Brinkelhoff. I learned Honkelbriff. Brinkelhoff is new to me, but this is part of our diatomic gas. So I can't just split this guy. So I'm going to do a little trick. And sometimes you might have to do this if you have a particularly hard combustion or decomposition product. I'm going to write a fraction here. I cannot leave it like this. I can't. It's not going to work. But I'm going to write 1/2. And if I write 1/2 O2, I actually go down. So let's add up my oxygens together again. So 12 from the CO2 plus 5 plus 1/2 times 2 is 1, 18. But I'm not allowed to have fractions. Not okay. So instead, I'm going to treat this like an equation, right? Remember, in algebra, you can always multiply or divide each side of the equation by the same thing as long as you do it to both. I'm going to write 2. So then that's going to come out as, actually, let me get a little, let me get my dividing guy out of the way. And then I'll write this in a different color. That's going to come out as 4 C3H5N3O9 times 2 times 3, 6N2 plus, you have to, everything gets multiplied by 2, 12 CO2 plus 10 H2O plus everything multiplied by 202. And then we can do a quick check. So how many carbons do we have? 4 times 3 is 12, and then we have 12 here. Perfect. 4 times 5 is 20. 10 times 2 is also 20. Perfect. Sort of scribbled out my 4 here. 4 times 3 is 12, and so is 6 times 2. And 4 times 9 is 36. So this is my last check. So 12 times 2 is 24 plus 10 plus the 2 from here comes out to 36. So this is balanced. We did it. It's a little bit tricky, and it's a little bit non-intuitive to try to fix this nitrogen first, because very frequently with elements like this, you want to fix whatever is alone on one side of the reaction last. That can help a lot. But here I could just kind of tell that it might be a problem. And I can just kind of tell, I mean, I tried to solve this multiple times before I recorded this video. So I've been through this equation, and sometimes it's just a matter of finessing and finding out what works. And it's a matter of finding these little tricks, as long as you come back and make sure all your coefficients are actually whole numbers at the end. All right, so let's do another one. Let's take a little brain break and do one that's a little bit easier and not so tricky. One day I'll be able to draw a straight line on my tablet here. There we go. So you might notice that this is iron, this is oxygen. It's a pretty typical reaction, and this is one form of rust, right? That's an iron oxide. So we can just balance this real quick. FeO, FeO. We only have 2 things in each of these. So 1 iron, 2 oxygens, 3 irons, 4 oxygens. And here we're kind of set up conveniently, because every element is on its own on the left-hand side of our equation. So I'm just going to fix oxygen first. It's just my choice. So this becomes 4, and this is my next fix, becomes 3, and that's it. 3 oxygen, 3 iron, 2 molecules of oxygen. Remember that this is a Hunkelbrief, and we get rust. That's a little quick one. Okay, so here is another equation to balance. This one is for this lead compound. It's a lead, tin, and oxygen compound, and it was actually for a long time, and still is, called lead tin yellow. And it was used in all types of famous paintings. It's very popular form of yellow, except that it's toxic, but you know, artists want the brightest colors. So I'm gonna draw our line, and you can see that this is kind of gonna be maybe a little bit messier than our rust equation. We've got different amounts of lead already. We got oxygen all over the place. So let's get to bookkeeping. Lead, 10, oxygen. So 3 lead, 1 tin, 6 oxygen. 2 lead, 1 tin, 6 oxygen. So first we have to make this lead common between them. So when I see a 2 and a 3, I know that I'm going to change it so that I get 6 almost every time. So 6, and then I have 3, 10, and now I have 3 times 4 is 12, plus 2 is 14. And then I'm going to do the same thing to fix my lead on this side, but it's a 2 here. So 6, there's no 10 in that species. So we get 2 times 4 is 8 plus 2 is 10. So now my lead is fixed, but my tin needs to be fixed. So I have 3 on this side and only 1 on this side. So I'm going to put a 3 here. So 3 tin. And now I have 8 oxygen plus 6 oxygen is 14 oxygen, right? If that's right, we're done. So 8 plus 6, we get 14, and we can check that all out. And this is our balanced equation to produce this product, which is our lead tin yellow famous pink pigment. So this is an equation or a reaction equation for the synthesis of this compound, which is Egyptian blue. It's the first synthetic blue pigment. And it was made and discovered in Egypt, and we lost it for a while, which was kind of a bummer because nobody had any good blue pigment. But we are going to balance the equation for that. And it does look like a mess. There's a lot going on here, but we know we can solve it because we already solved the nitroglycerin decomposition reaction. We already said that if we can solve that one, we can solve anything, right? So we're going to come through here and write down our inventory. 2 coppers, okay? 1 calcium in our calcium carbonate. And then 1 silicon in our silicon dioxide. And then this one I miss sometimes. Can't miss it. So carbon here and a carbon here, 2 carbons. And then 2 hydrogens. And then we have a lot of oxygen. And I said it once before, and I said it again, I will use a calculator to help me keep track. So 3 plus 2 plus 2 plus 3. It's not always that the addition is hard. It's that the keeping track as you're adding them all up can be a little bit difficult. So 1 copper, 1 calcium, 4 silicon, and then got 1 carbon here. We're not missing anyone, 2 hydrogens, and then 10 plus 2 plus 1 is 13 oxygens. So who are we going to fix first? Copper. So we have 2 coppers here. 2. I don't think that made it any better. 2 and 1. So I'm going to fix copper first. And I know if I put the coefficient here of 2, I'm going to have a lot of other stuff to recalculate. So let's go ahead and do that. Now we have 2 calciums, 8. And then we went from 13 to 23, because 2 times 10 is 20, plus 2 plus 1 is 23. But we fixed our copper. And now what we've done is we've messed up our calcium, and we've messed up our silicon. So there's a lot of back and forth in this one. So let's go ahead and fix calcium next. So 2. Now we have 3 carbons, right? 2 from here, 1 from here. And then let's go back through and keep track of all of our oxygens. So 6 from here plus 2 from here plus 2 plus 3 gives us 13, yeah? 6 plus 2 plus 2 plus 3, 13. Okay. So copper's fixed, calcium's fixed. Next one we got to fix is going to be our silicon. So let's fix that. I'm going to do that by putting an 8 here, because I know I have 8 on this side, right? I'm going to fix this to 8, and then I'm going to have to calculate my oxygens again. So 8 times 2 is 16, plus the 6 from the calcium carbonate, plus 2 plus 3. So then I get 27 over here. So now what is left? Copper fixed, calcium fixed, silicon fixed. Carbon is still messed up. Hydrogen is okay. And then oxygen. So let's go and fix carbon. And the only place we have carbon here is in carbon dioxide. So I'm going to add a 3. So we get 3. And then let's calculate 2 times 10 is 20. Plus 6 plus 1 is 27. So that's our total balanced equation. So our coefficients are 1, 8, 2, 2, 3, and 1. So it was hard, but by finding which ones were the weirdest to fix, everything sort of falls into place when you work your way down to carbon. So it can also be helpful to, think about what order you want to fix things in. And if you get stuck completely on one order, sometimes I just turn over a new sheet of paper and try a different order. I think the first time I tried solving this, I fixed silicon first and it worked, but it took a lot longer to get there. So there are different ways and it takes practice.